So to recap, Chapter 5 is broken up into 3 different videos. In Part A, we talked about the mole, which is a word we use to represent 6.02 times 10 to the 23 particles. And then we moved into working on balancing chemical equations. So Part B is going to talk a little bit about some of the different types of reactions that we see in chemistry. Most chemical reactions can be grouped into one of these 4 or 5 categories. There's actually more, but these are some general categories that we use often. The first one is combination. I'm going to go over these. I'll just do it quickly here. I think it's good for your brain to hear it a couple times. In a combination reaction, you're going to have 2 or more things combining to make one. So you're always going to have one thing to the right of the arrow. The second reaction we're going to look at is called a decomposition, where you always start with one thing to the left of the arrow, which is going to break up into smaller pieces. Single replacement, probably one of the more complicated reactions because you have to pay attention to what's replacing what. How you're going to be able to identify a single replacement reaction is that you're always going to have a compound and an element. Okay, and the element is going to trade places with one thing that's in the compound. Now, where it gets a little bit tricky is you have to focus in on the variables I've used here to symbolize these reactions. The C is the element because it's all by itself. You have to pay attention to whether that C is a metal or a nonmetal. If it's a metal, it is going to trade places with the metal in the compound. If it's a nonmetal, it's going to trade places with the nonmetal. So the other thing you need to remember is that when you're looking at the compound, that you always write a cation first and the anion second, or the metal first and the nonmetal second. Okay, so if C is a metal, it's going to trade places with the first thing in the compound. If C is a nonmetal, it'll trade places with the second thing. The fourth reaction we're going to look at is called double replacement. Sometimes it's pronounced double displacement, so either one are the same. In a double replacement reaction, you're going to have 2 compounds on the left, and 2 things are going to trade places. So the metal in the first compound is going to bond to the nonmetal in the second one, and the metal in the second one will bond to the nonmetal in the first one. So the tricky part about writing a double replacement products are that you have to remember that in ionic compounds you always write the metal first and the nonmetal second. Okay. And then the last reaction we're going to look at are what we call redox reactions. Okay, addition reactions, which are combination reactions, which are also called addition reactions. You're going to have 2 or more elements forming one product, or some simple compounds combining to make one product. In either way, you're going to notice that you always have one thing to the right of the arrow. So you have several things combining to make one thing on the right. Here is an example of elements combining. So magnesium and oxygen is combining to make it magnesium oxide. Another example, so we have sodium and chlorine combining to make sodium chloride. This is an example of just smaller molecules combining to make one molecule. So if you look at what is in common in all combination reactions is we only have one compound to the right of the arrow. Compound reactions are also known as addition reactions. In a decomposition reaction, one substance is going to split into 2 or more simpler substances. So an example here would be mercury oxide breaking up into mercury and the oxide elements. Here potassium chlorate is breaking up into some smaller compounds, potassium chloride and oxygen. Once again, what's in common in a decomposition reaction is one thing to the left of the arrow. So a learning check for you to try. Classify the following reactions as either combination or decomposition. So I'm just going to either put a C or a D to the left. Let me get my pen. Okay, when I look at A, I see 2 things on the left but only one on the right. This is my giveaway. Only one thing on the right means that we have a combination reaction. My hydrogen and bromine are combining to make the hydrogen bromine. When I look at B, I only see one element on the left, or one compound on the left that's breaking up into some smaller compounds, so that is going to be a decomposition. And in C, I have some smaller things combining to make one thing on the right. So that's a combination, also known as addition. Okay, single replacement reactions. Remember that the metal replaces the metal and the nonmetal replaces the nonmetal. In a single replacement reaction, one element takes the place of a different element in a reacting compound. So here is my example. The variables I have here is A is by itself. So in this particular example, A is the element, and B and C are the elements making up the compound. So remember, just by looking at this B and C, I can tell that B must be a metal and C must be a nonmetal, because we always write the metal first. So when I look at this, actually I'm going to ask you, tell me, just by the way this has traded places, do you think that A is a metal or a nonmetal? And I'm hoping that you can say, well, since the A ends up in the first place here, we always write metals first, so A must be a metal. So sure enough, the A and the B traded places in this single replacement reaction. So here's an example where I've got zinc as the element and hydrogen chloride as the compound. Now zinc is going to trade places with one of them in here. Well, the zinc, since it's a metal, is going to want to bond to the chloride, which is the nonmetal. So the zinc is going to trade places with the hydrogen, and the zinc is going to become the zinc chloride, and then hydrogen is going to be off by itself. Remember, hydrogen is diatomic, so when you write hydrogen by itself, it has to be in a group of two. It is one of the Hankel-Briefs, where your Hankel-Briefs, when they're in a compound, do not need to be in a group of two. So that's an example of a metal replacing the metal. It's a little bit tricky because hydrogen technically isn't a metal, but remember, it's an exception. Here, the element that's by itself is the bromine, so that's a nonmetal, so it's going to trade places with the nonmetal on this compound. So the nonmetal over here is chlorine. So the bromine and the chlorine are going to trade places. So the sodium will now be bonded to the bromine, and the chlorine is going to stand alone. Here's an example again where we have to write the element by itself as a diatomic, because chlorine is a diatomic, where in sodium chloride there was only one of each. And the bromine, which is a Hankel-Brief diatomic, is you don't have the two over here. So here's a learning check. Complete and balance the following single replacement reactions. So if we're going to start here, I am going to bring down the names into a formula. So zinc is a capital Z, lowercase n. Whenever I'm writing an element by itself, I always pause and think through my Hankel-Briefs. Is zinc one of the Hankel-Briefs? No. So I'm allowed to write it by itself. It's not diatomic. Here is an ionic compound. So I do not want to write the formula unless I'm looking at the ions. So above here, I'm going to write down maybe I'll go up here, I've got a little bit more space. Silver is a capital A, lowercase g. Nitrate, notice it ends with 8, which means it's a polyatomic ion. So you would want to look at your information sheet and find nitrate, and it's going to tell you it's NO3 with a -1. To figure out the charge on silver, it's a transition metal, so you might think that I should be giving you the Roman numeral in here, but remember, it's one of those special ones I told you should memorize, that aluminum, zinc, cadmium, and silver have a fixed charge. So look on your information sheet, and it's going to tell you that silver is a +1. So when I do my crossing method and I would bring those ones down, I'm going to say I need 1 silver and 1 nitrate. Okay, now I need to do my displacing. So zinc, the element by itself, is a metal, so it's going to trade places with the silver. So the zinc is now going to be bonded to the nitrate. So before I write down my zinc nitrate, I need to think through the charges. So zinc is one of those 4 special ones: aluminum, zinc, cadmium, and silver. So on your information sheet it tells you it's a +2. And I'm going to put that together with my nitrate, which we already decided was a -1. So that means I need 2 nitrates, but only 1 zinc. So 1 zinc, 2 nitrates. You always have to put parentheses around your polyatomic ion if you need more than one of them. So that's my zinc nitrate, and then the element that's going to be by itself is now the silver, because the zinc and silver traded places. So this is my first step in writing a balanced chemical equation, is take the time to write your formulas correctly. Think through the Hankel-Briefs, and when you write an ionic compound, I recommend writing your ions first. Now we have to balance. So on the left side of this arrow, I have 1 zinc, and on the right side of the arrow I have 1 zinc. So my zinc is balanced. Looking at my silver, I've got 1 silver on the left, 1 silver at the right. Keeping my polyatomic ions together, how many nitrates do I have on the left? I have 3 oxygens, but I only have 1 NO3. Over on the right I have 2 NO3s. So I need to put a 2 coefficient in front of the silver nitrate to give me 2 nitrates. So now my nitrates are balanced, but I've messed up my silver. My silver is no longer balanced. So I have to come over here and put a 2 in front of the silver, so that silver will balance. So there's a balanced equation for that single replacement. Here is an example where a nonmetal is going to replace a nonmetal. So let's go ahead and start here. Chlorine is capital C lowercase l. Whenever I write an element by itself, I think, is it a Honkelbrief? Sure enough, chlorine is one of the Honkelbriefs. Sodium bromide, this is an ionic compound, so I'm going to take the time to do my ions first. Sodium is in the 1A family, so it's a +1. Bromine is in the 7A family, so it's going to be a -1. So when I do my crossing method, I just 1-to-1 ratio, 1 sodium to 1 bromine. Okay, single replacement. I have to think about what the chlorine is going to trade places with. Well, chlorine is a nonmetal. What is my nonmetal over here with my sodium bromide? The nonmetal is the bromine. So the chlorine and the bromine are going to trade places, and my chlorine will then be bonded to my sodium. So if I want to put my sodium with my chlorine together, I'm first going to draw my ions. So sodium's a +1 because it's in the 1A family. Chlorine's a -1 because it's in the 7A family. So when I do my crossing and reducing, I just end up with 1 sodium and 1 chlorine. You can show that one, or you do not have to. Okay, so, and then I have bromine all by itself because bromine is the element that got traded places with. Is bromine a Honkelbrief? Yes, it is. So I have to put the 2 here. Okay, so that's my first step. I've written my formulas correctly. Now I'm going to go put my coefficients in. I have 2 chlorines on the left, only 1 chlorine on the right. So I'm going to put a 2 coefficient. Focusing on my sodiums, 1 sodium on the left, 2 sodiums on the right. So I'm going to put a 2 in front of my sodium bromide. That's going to give me 2 bromines on the left because that 2 gets distributed, and I have 2 bromines on the right. So I am now balanced. So my first example was showing how a metal replaced the metal. So in this case, the zinc traded places with the silver. Here, my chlorine traded places with the bromine. In a double replacement reaction, 2 elements in the reactants are going to trade places. So single replacement, you just have the replacement of one from the compound. But here we're going to, replace both things. So it's always going to turn out that the metal in this one, the first one in this one, is going to bond to the second one over here. And the second one in the first one is going to bond to the first one. But the problem is this first one's a little bit tricky. I mean, the second one's tricky. When you put the B together with the C, you better make sure that you write the B first. The C first, because it is the metal, followed by the nonmetal. So here's an example of that. The silver ends up bonding to the chlorine, and we get silver chloride. And the nitrate goes to the sodium, but they wrote it with the sodium first, so you have sodium nitrate. Double replacement reactions are also known as exchange reactions, so depending upon which textbook you're using. So here's a learning check. Go ahead and pause this video and see if you can do this one. Now remember, when you're writing an ionic compound, I first recommend that you write your ions first. So zinc is one of those 4 special transition metals that has a fixed charge. Oops, I was just about to do a minus sign. I'm going to caught myself. Okay, so zinc is a 2+, because all metals become cations. Sulfide, this ends with IDE, which means it's not a polyatomic ion. I have to look at my information sheet. So sulfur is in the 6A family. So your information sheet tells you all nonmetals in the 6A family become a 2-. Now when I cross, I'm going to end up bringing this 2 down here, and this 2 down to be the subscript of zinc. But they're going to reduce. 2 and 2 reduces down to 1 and 1. So zinc sulfide is just 1 zinc to 1 sulfur. To do my hydrogen chloride, I'm going to go like hydrogen is in the 1A family, chlorine is in the 7A family, so that's just going to be a 1-to-1 ratio. And I'm going to do an arrow. And now this is double replacement because I have 2 compounds. It would be single replacement if I had an element in a compound. But I have 2 compounds. So my first metal here is going to go to the nonmetal over here. And my nonmetal is going to bond to, well, remember hydrogen's an exception, but we're going to think of it as a metal in this case. When I put the zinc and the chlorine together, remember I don't want to do that until I'm looking at the charges. So zinc has a fixed charge of 2+. Chlorine is a -1, so when I crisscross, I only need 1 zinc, but I need 2 chlorines. And then when I put the hydrogen and the sulfur together, I have to remember to write the hydrogen first. So how many hydrogens do I need? Well, it depends upon what the sulfide charge is. Sulfide has a 2- charge, so I'm going to need 2 hydrogens. And then I write down the sulfur and ask myself how many sulfurs do I need? And since hydrogen is a +1 charge, I'm only going to need 1 sulfur. So there is the first step where I've written everything correctly. Now I need to go and balance. Okay, so it looks like my zincs are balanced. 1 zinc on the left, 1 zinc on the right. 1 sulfur on the left, 1 sulfur on the right. Hydrogen, I only have 1 hydrogen on the left, but I have 2 hydrogens on the right. So I'm going to put a 2 in front of my hydrogen chloride. And then two chlorines on the left, 2 chlorines on the right. So I am balanced now. Here's another one to try using polyatomic ions. I actually have the answer here on the slide. So your first step would be to write the formulas correctly. So you'd want to write down the ions and do the crossing method, and you'd come up with, this would be step 1. Here's your formulas. Step 2 then is going to be, well, one of the methods is to focus on your more complicated molecule. So let's go ahead and start by balancing the polyatomic ions. Well, the polyatomic ion in here, if we look at the first one, magnesium chloride does not contain any polyatomic ions, but sodium phosphate does. So the polyatomic ion is the phosphate. So on the left, I only have 1 PO4, and on the right, I've got 2 PO4s. So to make this balance, I'm going to put a 2 coefficient in front of the sodium phosphate. Okay, so now the phosphates are balanced. So now that we've got the more complicated part done, let's go ahead and do the magnesium and the chlorine. So I've got 1 magnesium on the left, 3 on the right, so we're going to have to put a 3 coefficient here. Chlorine, once I put the 3 here, that's going to make 6 chlorines. And so over here, I'm going to have to put a 6 here to make 6 chlorines. And you're going to notice then that that's going to make the sodiums balance. 6 sodiums, 6 sodiums. So everything will balance now. Okay, learning check. Classify the following reactions as either a single replacement or a double replacement. So I'd put an S or a D to the left of the letter. See how you do. In this first one, I see an element reacting with a compound. So that is a giveaway that we're doing a single replacement. And in this case, it is the metal that's going to replace. We're going to think of the hydrogen as going to be the metal. Okay, here I see the sodium sulfate as a compound and silver nitrate as a compound. So this is going to be double replacement. Looking at C, carbon is an element, iron 3 oxide is a compound, so this is going to be a single replacement. Okay, so the last category of reactions is redox. I have it abbreviated here. I'm not sure if I show you it non-abbreviated in a coming up slide, so I'll show you it here. The redox is short for, this is equal to oxidation, reduction, reactions. So that's kind of a mouthful. So chemists just usually say redox and saying oxidation, reduction, reactions. So in a redox reaction, it's going to be a reaction that involves oxidation and reduction, where the electrons are transferred from one element to another. So in the last few examples we didn't really focus on whether electrons were exchanging places. We just kind of focused on the changing arrangements of the atoms. Okay, so here's a little bit of terminology. I wish I had underlined this because I do want you to have this memorized. Reduction is gaining electrons, and it's going to be a decrease in charge. That sometimes helps you think about why it's called a reduction. So, for example, if I have, let's say, let's just do chlorine, a chlorine atom turning into a chloride. This would be, this chlorine gained an electron, and sure enough, there was a decrease in charge. I started off as being neutral, and it ended up becoming a -1. So moving left along the number line would be decreasing in the charge. So for reduction, there's going to be the gain of electrons. That's the biggie. During the reaction, sometimes you're going to notice that it's reduction because there's a decrease in oxygen or an increase in hydrogen. So those are the 3 different ways you're going to be able to identify a reduction. Oxidation is going to be, let me go through this. So here was the chlorine, where the chlorine is gaining an electron and becoming a -1 charge. So note the electron on the left of the arrow means that it's gaining electrons. So the chlorine gains an electron to become the chloride. In oxidation, let me underline it so you know it's a vocab word. In oxidation, it is always the loss of electrons. And what's going to happen is the charge is going to increase then. It's going to move right along the number line. It's going to get more positive. Sometimes you're going to notice it as an increase in oxygen or a decrease in hydrogen. So the main thing you want to memorize is oxidation is the loss of electrons, but it is also the increase in oxygen or the decrease in hydrogen. And here's an example of that. Zinc metal is losing 2 electrons as it becomes the zinc ion. Notice the charge, it went from being neutral to being a 2+, so the charge increased. That will happen in an oxidation reaction. A couple things. I'm going to tell you how I tried to remember this. I have a couple little acronyms for you. There is a saying that says, Leo the lion says grr. And what you focus on is the Leo and grr. This is loss of electrons is oxidation. Gaining electrons is reduction. So that sometimes helps students remember that. Or another acronym here is oil rig. Some students just like to memorize oil rig, which stands for oxidation is losing electrons and reduction is gaining electrons. So that helps you out with the first, this first part, the gaining electrons or the losing electrons. When I was trying to help myself remember the gaining oxygen or losing hydrogen parts, I had thought of, this might help out some of you, I'm going to go to the bottom of the slide here. I had known from my life experience that metals get oxidized, that when something is rusting, I had heard somebody say that the iron's being oxidized. So when I thought about that, the iron reacting with the oxygen in the air turning into rust, I knew that the iron was being oxidized, and what's happening here is my iron is gaining oxygen. So that was all I needed to memorize to get all the rest of these correct, because if oxidation, so let me write this down, if oxidation is either gaining oxygen or losing hydrogen, okay, so then reduction is just the opposite of that. Reduction would be losing oxygen or gaining hydrogen. So just kind of focusing on that resting equation helped me remember the rest of those. So reduction cannot happen without oxidation. They're one and one. One cannot occur without the other. If something's losing electrons, there has to be something there to gain the electrons. So reduction and oxidation always go together in a chemical reaction. If one reactant is oxidized, there better be something there getting reduced. So here's an example. I have zinc reacting with copper sulfate. Now notice, thinking about the other categories, is this example a combination, decomposition, single replacement, or double replacement? And I'm hoping you said it's a single replacement because I have an element and a compound, and the zinc is trading places with the copper. So some of the previous categories can be oxidation reactions. Just to help you out, the single replacements will always be a redox, and double replacement will never be redox. So those two are always the case. The combination and the decomposition can, or doesn't have to be. So let's see. So, but this particular single replacement reaction is also a redox reaction, and the way we know it is because the zinc over here is a neutral element and it's turning into an ion. So it went from being zinc neutral to being 2+, which means it must have lost 2 electrons. So losing electrons is oxidation. The copper, since it's in a compound, is an ion. So it's a cation with the 2+ charge. And it ends up becoming over here where it's neutral. So its charge was reduced. It gained electrons. So since the copper 2+ is gaining 2 electrons to become neutral, we say that the copper 2+ was reduced. So one more time, the zinc is what was oxidized. It is this neutral zinc metal that lost the electrons, and it's the copper 2 ion that gained the electrons. So the copper 2+ is what was reduced, and it's the zinc metal that was oxidized. So here's something that might help you to be able to quickly identify whether something is a redox reaction. Remember that if it's an uncombined element, it's going to have a 0 charge. So some examples of uncombined elements would just be any element written by itself or your diatomics. All of those are going to have a zero charge. And then remember that elements that are combined with other elements are going to have a non-zero charge. So sometimes you don't even want to take the time to figure out what the charge is. You just say to yourself, wow, the copper is in a compound, so it's going to be a cation. And I'm not going to take the time to figure out whether it's a +1 or a +2. I just know that it has a charge, and my sulfate's going to have a negative charge. So any of these compounds are going to have charged particles in them. So that sometimes helps make it a lot quicker to help you decide whether something is a redox reaction. So which of the following are redox reactions? Hint, anytime there is an uncombined element on one side and then you see it combined on the other side, then you know it's redox. If it's not as simple as that, you're going to have to assign charges and see if the charges had changed. If there's any change in charge, that's your indication that it's a redox. So when I look at A here, A is going to be the quick example where I can say, wow, I see aluminum by itself on the left and it's in a compound on the right, so this is redox. So it says which of the following is redox. A is a redox. I look at B, and that is a little bit more complicated. I mean, I don't have anything by itself on one side and then in a compound. So to prove that they did not change, that it's not a redox, you would have to, assign charges. We'd have to say the copper is the barium is a 2+, the chlorine ion is a 1-, sodium here is always a +1, the sulfate polyatomic ion's a -2. Over here, barium's a 2+, sulfate again is a -2. Sodium's a +1 and the chlorine is a -1. So if you notice, nothing changed charges. Barium stayed a 2+ the whole time and chlorine stayed a 1-. The fast way to see this is if you memorize that double replacement reactions are never redox. So that's what I would have done. I would have said, oh, this is just double replacement, and said it's not redox. When I look at C, I see aluminum by itself over here, and here it's in a compound. So that's a quick way of saying, it's redox. I'm not even going to take the time to assign the charges. Okay, so here's just a summary slide. I'm taking you back to the original definition, okay? Oxidation is always the loss of electrons. Okay, if something loses electrons, it's oxidation. Also, if you notice that there's an addition of oxygen or a loss of hydrogen, that's another way of noticing that it's an oxidation reaction. Reduction is always the gain of electrons, and sometimes you're going to notice that by a loss of oxygen or a gain of hydrogen. Now that's hard for some students to see, the oxygen and hydrogen. They might say, well, why is that not always the case? Like over here, loss of electrons, it's an always word. Oxidation is always the loss of electrons. This, looking at the oxygen and hydrogen, is just a quick way of seeing it. It is true that there is still transfer of electrons happening. It's just harder to see when you have organic molecules, and sometimes it's easier to see if you just look at the oxygen and hydrogen. But to kind of prove to you that, that there is still a transfer of electrons, I'm going to walk you through this one example. So why are reactions that involve the gain or loss of hydrogen or oxygen considered to be redox reactions? So let's go ahead and just look at a very simple reaction where there's changing of the hydrogens and the oxygens. If we look at hydrogen and oxygen gas combining to make water, the hydrogen reactant, so we're looking right here, when it turns into the water, what happened to it in terms of hydrogen or oxygen? Did it gain oxygen? Did it lose hydrogens? What happened? Well, the hydrogen gas ends up gaining oxygen. So we would say that the hydrogen then is oxidized because it went from not having any oxygens to having an oxygen. If we focus on the oxygen here, when it turned into the water, the oxygen gained hydrogen. So that would be our definition of reduction. So we would say that the oxygen was reduced because it gained hydrogen. The hydrogen was oxidized because it gained oxygen. I didn't say that wrong. Okay. So that doesn't necessarily prove to you that there was a transfer of electrons, so let's look at it a little bit more closely. If we focus on the hydrogen, which was neutral, turning into a plus charge in the water, so if we think of the water as having hydrogen with its plus and oxygen with its 2-, I'm oversimplifying here, but I want you to see the point. The hydrogen, since it was all by itself on the left side and then it's in a compound on the right, going from being neutral to a +1, it must have lost electrons. So it is oxidation. If we focus on the oxygen, it goes from being neutral to having a 2- charge. Where's my pen? So here the oxygen's neutral. Here it has a 2-, so it must have gained 2 electrons, and gaining a lot electrons is reduction. So here's just a couple more examples. Combustion of a fuel. So here is an example of methane combusting, making carbon dioxide and water. So this is complete combustion. In this case, the hot carbon, if we focus on the carbon here, as this carbon changed from the reactant side to the product side, what happened to it? Well, I can see it lost hydrogen right off the bat. And another way I could look at it is that it gained oxygen. So both of those are a way of coming up with the fact that it was oxidized. Gained oxygen or lost hydrogens. So the carbon was oxidized. If we focused on the oxygen here, it went, you can focus on it either, well, it's not going to help us if we go that way, but if we go here, we can see that it gained hydrogen. So since the oxygen gained hydrogen, we're going to say it was reduced. Another example would be cellular respiration, where we have glucose combining with oxygen to make carbon dioxide and water. And if we look what's happening to the carbon here, I can see it quicker by seeing that it lost hydrogen. So as I look at it from going from this molecule to the carbon dioxide, my glucose has hydrogen in it, and my carbon dioxide doesn't have any hydrogen. So the carbon, I can quickly see that it lost hydrogen, so it's oxidation. But we could also say that the carbon here is bonding to the oxygen, so it's gaining oxygens. If we focus on the oxygen, it is gaining hydrogen, so we say that the oxygen was reduced or went through reduction. So here's a learning check for you to give it a try. Go ahead and pause the video and see if you can come back and get it right. It wants to know which reactant above was oxidized and which one was reduced. So if we focus on our first molecule here, how does it change as it goes from the reactant side to the product side? Well, first of all, nothing happens to my oxygens. The oxygens stay the same, 4 in each molecule. My hydrogens, however, go from having 6 on the left side to 4. So this particular molecule lost hydrogens. And that is one of our definitions of being oxidized. So we would say the reactant that was oxidized was the C4H6O4. Now I could really stop there, assuming I did this right, and said the other guy must have been reduced, because redox reactions always go hand in hand. But let's prove it to ourselves. So this FAD molecule ends up gaining 2 hydrogens. So gaining hydrogens is being reduced, so we would say that the FAD was reduced. All right.